Welcome to lesson number 3 of the course on industrial automation and control. So, in this course, in this lesson we are going to start at level 0 of the automation pyramid, and in particular we are going to look at measurement systems or sensors. So, before we are going to look at these measurement systems for a few lectures to come. So, before we do that, let us first look at a general measurement systems and try to understand its characteristics. So, that is precisely what we are going to do today. So, in this lesson we are going to look at measurement systems characteristics, and the instructional objectives are the following. First of all, the most important thing is to learn is what is known as the static characteristics of sensors and instruments, and then we understand what is meant by calibration and how do we characterize errors, describe the response of first and second order sensors to dynamic inputs, that is most important for control, and finally look at some industrial sensor specifications. So, let us first look at the general structure of a measurement system. So, all measurement systems can be thought of being made up of one or more of these blocks. So, here is the so here we have the actual measure end, whatever signal we are trying to measure, pressure, temperature, that is the signal which is affecting the sensing element. So, there is a sensing element. Actually, sensing is a process of continuous energy conversion from any form depending on what we are trying to measure. So, from mechanical form or from thermal form or from optical form to finally to an electrical form and then the electrical form gets finally transformed further to digital forms, etc., before their output. So, through these blocks that conversion takes place. So, here you have the measurand or the input, which is the true value. So, the real pressure or the real temperature, which is the sensing element which exists at the sensing element. Then the sensing element does the first round of conversion and brings it generally to some sort of an electrical form, either in the form of electrical parameters like resistance, capacitance changes, or in the form of voltages and currents, which have to be further manipulated by electrical circuits called signal conditioning elements, and sometimes amplified, sometimes the conversion from resistance to voltage. So, generally at this level it is in a standard electrical form of voltage, but then some further signal processing goes on to remove noise, to make it linear and things like that. Some of it can be analog, some of it can be digital, and then finally it goes to the data presentation element, or where the data is utilized. It can be presentation or application element. So, it can be a display, or it can be a recorder, or it can be a controller. So, this is the general structure of a measurement system. For example, if you take an example, for example, here is a weight measurement system. So, the input is the true weight, which is sensed by a mechanical member called the load cell, which converts it to strain. That is sensed by another member called a strain gauge. We will see all these sensors in our future lessons, which converts it to a resistance form. So, you see that even there are two sensing elements. The first sensing element converts weight to strain, the next one converts strain to resistance, and then we feed it to an electrical circuit called the Wheatstone's bridge, which converts this resistance change to a low level voltage, millivolts. So, this is these are signal conditioning elements. Then it goes to an amplifier, which amplifies it to standard voltage ranges like 0 to 10 volts. Then it goes to, if we most often it is very convenient to have digital signal processing. So, we can make it through an AD converter, then input it into maybe some microcomputer and do some digital signal processing, and then finally send it to in this case a display. So, you get a digital display of the reading along with units, right. So, that is some more data processing. So, this is how real measurement systems looks like. So, it is basically a cascade of several blocks, including the sensor, the signal conditioner, plus some computing elements like the signal processor. So, sensing is actually extremely important in automation from various points of view. Firstly, in product quality control, because the product quality is actually assessed by sensors themselves, by some sort of instruments. In process control, so if you have a rolling mill and if you want to control the roll thickness, then you have feedback, or most of all process control is actually closed loop feedback control, about which we are going to learn in the future lessons. So, for that a critical element is the feedback element. So, the variable which is being controlled, it may be thickness, it may be temperature, whatever, has to be continuously fed back using a sensor in the sensor of the control system, and the performance of the control system is actually critical to that of this sensor. So, sensing is of primary importance in control. Then process monitoring and supervision. So, all kinds of coordination between machines, then fault detection, safety measures, all this can be done, plus providing energy efficient optimal set points. For doing all this we need sensors. And finally, we also need sensors for manufacturing automation. So, as we will see when we will see how the manufacturing automation systems can be put together using let us say programmable logic controllers, then you will find that they use various kinds of sensors extensively, sensors like limit switches, pressure switches, contacts, etc. So, so sensing is extremely important in automation. Now, so in this lesson we are going to see that if you look at a sensor as an abstract element which gives you a value, which gives you the information about a physical quantity, then we need to know how to characterize the behavior of this device called the sensor or the instrument. So, we need to understand about instrument characteristics, and instrument characteristics can be of two types. The first is the static characteristics. Static characteristics implies that of an instrument are concerned only with steady state readings. So, if you it says that if you apply a 1 volt signal, do you get a 2 volt signal. So, we are just saying that if we apply, let us say to a temperature sensor, if we apply 100 degree centigrade, what is the output voltage. Now, we are not concerned with the fact when we are discussing static characteristic is that how the temperature came from whatever was, let us say, the room temperature 200 degree centigrade, how much time it took, what was exactly the way the voltage rose. We are not asking about these things, we just want to know that if you apply 100 degree centigrade, eventually the temperature settles at what value. So, that would be a static characteristics. Now, static characteristics are important for indicating instruments, because indicating instruments are generally concerned with steady state values, or for instruments where the dynamics is actually very fast, that is, this settling from whatever was the temperature to the 100 degree centigrade temperature is so fast that for all practical purposes we can neglect the way the temperature rose. That does not concern us. So, in such cases the static characteristics is of importance, while there are cases where dynamic characteristics is also important, especially in control, because as we shall see later that the performances of control loops, for example, when you are trying to control the essence of feedback control is that, suppose you are saying that this temperature should be maintained at 100 degree centigrade. Now, if the temperature sensor has a 2 degree centigrade error, by which I mean that suppose when the temperature is 98 degree centigrade, the sensor is telling you that it is 100 degrees centigrade. It is giving you a wrong information by which is wrong by 2 degrees. Then the controller has no way of knowing the actual temperature 98. It actually thinks that it is 100 degrees centigrade and it tries to maintain it at that temperature, while the actual temperature stays at 98 degrees centigrade. So, you have a steady state error, right. So, you have a real error, that is that physical real temperature will be 98 while the controller will think that it is 100. So, such errors occur due to controllers and due to errors in sensors, number 1, and number 2 is that now these errors can sometimes be reduced by designing the gains. So, it sometimes happens that we need to not only maintain fixed temperature, sometimes we need to track temperatures. So, in such a case, if we do not get the readings as they are existing, then what happens is that the temperature develops what is called a phase lag, that is the controller develops a phase lag, and it will not be possible to exactly track moving commands. So, in such cases dynamics of the sensors are actually important. So, we will look at both sensor and both static and dynamic characteristics, and before we look at this characteristic we need to understand how they are obtained. So, they are actually obtained by a process called calibration. So, basically a calibration is we are saying that if the true value is so and so, what is this? So, calibration is basically when you say characteristics of an instrument, what you mean is what is the input output characteristic. So, if the true value is so and so, what is the output? That is what is essentially to be determined. Now, the point is that the true value can never be known. So, therefore, how do you assess the true, how do you get the true value? So, essentially what we have to do is that we have to measure the true value again using some other instrument which for scientific and technical reasons we actually believe to be much more accurate. So, it is always calibration is essentially a comparison between the instrument that is being calibrated and another instrument which is assumed to be the true value. So, such instruments depending on the calibration situation, for example, if you are calibrating there is actually a calibration chain, in the sense that when you are calibrating some instrument in the factory, it is not possible for all variables. There are some very accurate instruments which are maintained in under special conditions in national standards laboratories. But when somebody is calibrating, let us say in a shop floor, it is not possible that every instrument will be calibrated against the national standard. So, therefore, there are secondary and tertiary standard equipment. So, anything will have to be calibrated against such an instrument. So, that is what it says, that with either a primary standard or a secondary standard with a higher accuracy than the instrument is to be calibrated. So, this is the essential scenario, that you have this is the sensor instrument which is to be calibrated. Now, the reading, first of all you are look at the fact that this is the measurand which you are measuring using some standard instrument, and you are thinking that this is the true value. This is an assumption. You are also measuring here this is not required. I do not know why this is connected. This diagram is drawn wrongly. So, the sensor instrument under calibration is giving a measurement. Now, this measurement again, for example, suppose it is a voltage, then how many volts it is, that again will have to be measured by some instrument. So, that may be this instrument, right. So, in that sense this is required. So, you have to measure the measurement. If the measurement is, for example, given in a digital form, then you do not need to measure it, then you can, so this may be there or not there. On the other hand, there are this sensor, this instrument reading or the measurement is actually a result of not only the measurement, it is a result of many other factors. For example, it may be a result of temperature. For example, if you take the weight measurement case, then the strain gauge resistance change is not only a function of the weight you put, it is also a function of the temperature, because every resistance has some temperature coefficient. So, if the temperature varies, then the resistance is going to change. Similarly, there are various kinds of interfering inputs, like for example, there may be some noise, there may be some noise induced from a power supply or from some power line, or especially in the industrial environment, there are plenty of noise sources, and these signals can also affect the sensor measurements. So, generally when you, to the extent possible, when you are trying to calibrate an instrument, you will have to also note what are the, for example, what is the temperature. So, if you so that you can actually apply the corresponding corrections, and you can characterize, when you are trying to characterize the instrument, you will also have to characterize its response with respect to these kind of inputs. I mean, in some cases it may not be possible to measure these kind of interfering inputs, and in such cases we try to ensure that these interfering inputs are not present. So, we do shielding, we actually do take it to a different setting and actually try to see what the sensor is doing. So, essentially we try to measure the measurand, we try to also measure the output of the instrument, and we try to measure modifying inputs like temperature, and then we establish the characteristics of the instrument. So, since the instrument must have been constructed to be, you know, relatively unaffected by modifying inputs. So, I mean, generally what is of much more importance, of primary importance, is to see how the instrument characteristics are dependent on the measurand, right. So, that is what we are going to look at mainly now. So, so this is what it says, that this is what I was talking about, that there are different standards of instruments. So, the instrument to be calibrated can be calibrated against a laboratory standard. Now, the laboratory standard instrument also has to be from time to time calibrated against, you know, other standards like, you know, secondary standards which are special instruments which can be, you know, existing in some test houses, and then so you from time to time you have to send these instruments to the test houses and get them calibrated. On the other hand, these test house instruments again have to be calibrated against, you know, some very accurate national standards. So in this way you have, you know, what is called a chain of standards of increasing accuracy, and at different levels you always calibrate according to a with respect to an instrument which is at the next level according to the chain. So, let us look at these static characteristics. So, we begin with span. So, it says that if in a measuring instrument the highest point of calibration is x2 units and the lowest point is x1 units. So, what we are trying to say is that the instrument has been used between 2 points. So, the instrument has been calibrated to work between 2 points, right, and this is so this is x2 and this is x1. Then the instrument range is x2, it is the highest, so it can work up to that value, and the span is x2 minus x1. So, if this is 200 degree centigrade and if this is minus 40 degree centigrade, then the range is 200 and the span is 240, right. So, that is pretty obvious. So, we have to remember these two details. Next, let us talk about one of the perhaps the most important parameter called accuracy. So, accuracy, if you see instrument specifications, they will be generally written as accurate to within x% of either reading or span. You know, sometimes they say reading, sometimes they say span. In fact, sometimes they also mention constant values, that is accurate within plus minus 1 degree centigrade. So, when this constant value, then since the span is a constant quantity, so you can always express it as a percentage of span also, right. So, if the span is 100 degree centigrade, then an error is of plus minus 1 degree centigrade can be expressed as 1% of the span. So, it is either a constant value, it may be expressed as a percent of span, or it is a percent of the reading. Okay. So, what it means that if a reading is 100 and if it has plus minus 1% of, let us say, span accuracy, then the reading is somewhere within, let us say, 99, and then the true temperature will be between 99 and 101 degree centigrade. And this, so at all points, so whatever reading you get, you can always, basically these are needed because the user of the instrument needs to know that within what values, so it gets a reading, but within what is the guarantee that the true value will be staying within certain limits. So, that limit is stated by accuracy, but then again the true value is unknowable, and it is actually what is stated is that with respect to the calibration. So, then the next point is linearity. You know, we generally want, although instrument calibrations will not strictly follow a linear curve, but still it is very useful to imagine the system as a linear one. So, you know, if you have so that you can very easily interpret the true value. So, if you have an instrument sensitivity of, let us say, 10 millivolts per degree centigrade, then if it gives a 25 millivolt signal, then you know that it is that the temperature is 2.5 degree centigrade. So, you can get it just by dividing by a number or sometimes adding another number to it. So, it is from that point of view, from the point of view usability, it is very attractive to express the characteristic as a linear one, but then it is not linear. So, therefore, while you mention a line which can be used for deducing the true value from a reading, you also have to give some bounds within which the true value will remain, because it is not exactly going to, because the instrument does not actually follow that line characteristics. The line is only an approximation. So, when you are telling the user to use the approximate model of the line for simplicity, you also have to tell him what is the kind of error that he or she can expect if she uses the linear model of the instrument. So, that is given by the measure of linearity. So, the linearity specification indicates the deviation of the calibration curve from a good fit straight line. So, now how do we obtain this straight line? We can obtain the straight line in various ways. So, one way would be this, that you actually perform some calibration experiments. So, you got these data points. So, you got these data points, these are experimentally obtained. So, for all you know, the true characteristic of the instrument, let me use a white color, that will be good. So, for all you know, the true characteristic of the instrument may be like this, and you are approximating it by the straight line. So, you have to also say that while if you use the straight line characteristics, then the true value is going to be within which limit. So, that is why when you say linearity, actually the linearity specification is actually a non-linearity specification, in the sense that it indicates deviation from linearity. So, it is defined as the maximum deviation of an output reading from a good fit straight line. So, obviously you want that. So, obviously you want that the straight line, that the linearity specification is small, so that you are telling that if you use that straight line characteristic, you are not going to have much error. That is what you are telling to the user. So that it is the smallest possible, you have to actually take all the data and make a best fit straight line, such that the sum of square of errors is the least, or something like that. So, that's linearity, that it is the deviation of the calibration data from some good straight line which you have obtained either by data fitting, or in some cases it may be obtained also in a different way. So, for example, in this case you can also obtain it, that's a simpler way, by taking the reading at the least value and the maximum value, and then simply assuming that the characteristic is going to be like this. Now, this is not the best fit line, probably for this curve the best fit line would have been like this. However, in some in some cases you can perhaps use this line, that's actually a simple thing if it does not matter. So, basically nonlinearity, whatever is the line, once you have fixed the line, the nonlinearity is actually this deviation. So, here it has the maximum deviation. So, the nonlinearity spec, or which is, I mean, we actually refer it to as a linearity spec, is actually deviation from that line, right. So, next we are interested in sensitivity. So, sensitivity is actually the slope of the line. So, if you have a calibration curve and then, so that will be the sensitivity, and if you have a calibration curve and then get a straight line, in case you have a linear characteristic, it will have one single sensitivity. If it is very nonlinear, then sometimes you may also express it as, so you can do various things. You can express, say, let us say 3 sensitivity figures. So, one sensitivity figure will apply in this range, the other sensitivity figure which is the average slope of the line in this range, and then another sensitivity figure which will apply in this range. Or you can, so basically sensitivity is the slope of the characteristics. So, depending on the nonlinearity, you can use multiple slopes on multiple ranges. Sometimes instruments do that. Similarly, we are also interested in what is called repeatability or precision, in the sense that we don't want that today we make a measurement of the temperature of boiling water. So it is giving me some reading. Tomorrow if I take that reading should be nearly same. It may not be exactly same, but it should be nearly same. So when it is very close, if you take multiple readings, if they are very close, then the instrument is said to be repeatable or precise, right. So repeatability of an instrument is the degree of closeness with which a measurable quantity may be repeatedly measured, right. So we go to the next one, which is resolution. This is also very, it says that how much of change in input will actually cause a detectable change in the output. So what is the smallest change in the input? So can we detect a change of 0.1 degree centigrade, or can we detect a change in 0.01 degree centigrade? For example, if you have a clinical thermometer, then you cannot possibly detect a change of 0.01 degree centigrade or 0.01 degree Fahrenheit. Generally they are calibrated in terms of Fahrenheit. So that is the resolution. If a temperature transducer resolution is 0.2 degree centigrade, then it is the smallest temperature change that can be observed. Okay. Similarly, we have, similar to the concept of dead zone, sometimes sensor systems will have dead zones. For example, we often find that these electrical meters, sometimes they will stick, any mechanical arrangement tends to develop something like a static friction, which also depends on many things like temperature, time, humidity and other things. So what happens is that till say if you have an ammeter, then till you send a certain amount of current, the torque is not enough to overcome static friction. So the needle does not move. So dead zone is the largest value of the measured variable for which the instrument output stays 0. So from 0 to that value, there is going to be no deflection, no reading, nothing. So that is called a dead zone. So what is the difference between the dead zone and the resolution? Dead zone is actually the resolution from 0, while resolution can be resolution from 24 to 24.1, 24.1 to 24.2, while generally dead zone is referred to from 0. So it occurs due to factors such as static friction. Similarly, sometimes we have hysteresis in instruments, so that if we have an increasing sequence of input values, if we are increasing the input from, let us say 0, 10 degree centigrade, 20 degree centigrade, 30 degree centigrade, they are increasing sequence of values, then we get one set of readings, while if we have a decreasing set of values, then we get another set of readings, and these readings are distinctly different, right. So, in that case we say that the instrument has a hysteresis. It can occur due to various factors like gears, gear backlash, or it can occur due to magnetic components, or sometimes due to hysteresis which occurs due to elasticity. So, due to such things the hysteresis can be there. So, what is, so this is the figure that we are saying that if x is increasing, then the readings that we obtain follow this curve, while if x is decreasing, they actually follow a distinctly different curve. So, if such behavior is demonstrated by an instrument, it is said to have hysteresis. So, next, so now the errors that we have, so we have actually typically an instrument is supposed to have a calibration curve, but the reading that it has may not exactly match with the calibration curve. It is, if you read out an ammeter, then it has some scale fixed, but if you send exactly 1 ampere current, then the needle may not stand at 1 ampere. So, this is the error. Now, the error is typically characterized as into two different kinds. So, since the instrument is actually assumed to be a linear instrument, so it is assumed that the error can be of two types. The first type is called bias or offset, which is a constant error which is going to stay throughout the range. So, maybe when you have a reading of, when you have an actual current of 2 amperes, your reading shows 2.5. When you have 3 ampere, it shows 3.5. When you have 10 ampere, it shows 10.5. So, you have a 0.5 ampere of bias, right. If you see ammeters, normal ammeters, you will find that such biases can be corrected by screwdrivers. They are also sometimes called zero adjusts. Similarly, there can be a gain error. So, you have a sensitivity, while we have a nominal sensitivity which is indicated by the scale, and your actual instrument sensitivity may actually deviate from that, and then you have a sensitivity or gain error, and the error in reading due to this gain error is going to be proportional to the reading. So, if you are measuring 10 degree centigrade, then the error due to gain error is going to be half of what you measure due to 20 degree when you measure 20 degree centigrade. So, we assume that the errors are of two kinds, and these typically in typical sensors and instruments, very often they can be corrected by electronic signal conditioning means. So that is what is depicted, that if you have a zero error, so that is a bias, and if you have a slope error, that is your gain error. Next is drift. So, sometimes what happens is that even if you correct at some point of time during calibration, even if you correct for the bias and the gain error, you have drifts in the bias and the gain. So again such bias and gain errors can develop due to variations in temperature, variations in time, or some other conditions. So the rate at which these will develop are characterized by a performance characteristic called drift.